So let us first draw the block diagram, the overall block diagram that we will have in this particular case. Because it's an interpolator, we will always have first interpolation taking place. This is I1 and followed by filter H1. The second stage will be interpolation by I2 and that will be followed by filter H2n. And this will be my final output y of n. So on the input side, if I write down the sampling rate, it is f0 equal to 44.1 kilohertz. After the first stage of interpolation, that means I1 and H1, the sampling rate will be, you can mention it the output of I1 or I can also mention it at the output of H1. The sampling rate will not change when the signal passes through the filters. F1 will be nothing but I1 into F0, which will be 2 into 44.1, so that will be 88.2K. And finally at the output side, F2 will be equal to I2 into F1. I2 is also 2 into 88.2 will give me 176.4 kilohertz, and this is what we are looking for. We want final output to have the sampling rate of 176.4 kilohertz, and that's how we had got the factor of 4. So it is very obvious that the final sampling rate will come out to be 176.4. Now let us go through stage 1 and stage 2 calculations. We will first consider stage 1. Please remember that for stage 1, I is equal to 1. Now there will be various steps like we had in case of design of decimator. Step 1 will always be about passband. Passband, like decimator, will not change here. So in this case, capital F will be greater than equal to 0 and less than equal to, the baseband frequency range goes up to 20 kilohertz. So that becomes my FP. Step 2 will be about stop band, and stop band will require stop band H frequency. So we say that stop band H frequency of ith stage is given as, so like the previous case, unlike the previous case, we don't write the entire range of stop band here. We will just calculate stop band H frequency directly. For the ith stage, it is given as f stop suffix I equal to 1 upon I into fi minus ii into fs by 2. So this is the formula that we use. In this stage, we are saying that I is equal to 1. So for I is equal to 1, we are going to get f stop 1 equal to, so wherever there is I, we will replace it with 1. So 1 upon 1 into fi will become f1 minus I1 into fs by 2. Now what are these values? 1 upon 1 will be 1. F1 is nothing but the output sampling frequency at stage 1, and from the previous block diagram that we had drawn, this is 88.2K minus I1 is 2. Fs is a constant value which is given as 44.1K divided by 2. So if you do this, the final answer will be 44.1 kilohertz. So that's my f stop. So we have got fp and f stop. This is what we require. One can draw the filter characteristics. Fp in this case comes out to be 20K and f stop comes out to be 44.1K. So in between the two, we have nothing but the transition width. So this is what we will do in step 3 now. In next step, we will calculate normalized transition width. So normalized transition width is nothing but delta fi. Delta fi will be nothing but, it will be the similar formula, maximum frequency of transition band, TB stands for transition band, minus minimum frequency of transition band, and this thing will be divided by output sampling frequency of that stage. This time please note that we consider output sampling frequency. So what will be my delta f1? Delta f1 will be nothing but, because we are at stage 1 right now, maximum frequency of the transition band is 44.1K minus minimum is 20K. So this is basically f stop and this is fp, and divided by output sampling frequency is f1, which is 88.2K. So this will approximately come out to be 0.273. So that's my delta f.